In this video, we're going to take a deeper dive into looking at circular motion, and this has tie-ins to a lot of physics formulas. When you look at uniform speed circular motion, we're going to look at it from a vector valued function approach here though. Let's start by sketching a graph of this function here, and notice that at the heart of it, it's a cosine and a sine function. We just have a lot of other factors playing a role, and we just need to study how those affect the graph that we're going to be getting, or the trajectory that we're studying. Time is our main variable, x and y are our follow-up ones, and this is our x out to here, this is our y out to here. And because we're looking at cosine sine, it makes sense to pick trig type functions or trig type values for our time, and 3 pi over 4 and pi, let's say, as the starting values. Remembering that cos of 0 is 1, sine of 0 is 0. That helps us to calculate our x component, which will be 3 plus cos of 0 times 5. That will be 5 plus 3, or 8. If we take a look at the sine component, it'll be sine of 0 is 0. That wipes out this entire term, and we're left simply with the negative 2 at time 0. So we'll have negative 2. At pi over 4, we need to be a bit careful, because we're going to take that time and multiply it first. So when t is equal to pi over 4, 2t's are going to be equal to pi over 2. And then just doing a quick change of our values up here, we're studying cos of pi over 2 and sine of pi over 2. Well, at those instances, those values are reversed. Cos of pi over 2 is 0, but sine of pi over 2 is 1. All right, let's take all this work back to the calculation here. When time is pi over 4, we sub it into here, we get cos of 2 times that, cos of pi over 2, cos of pi over 2 is 0. So we're going to end up at 3. And similarly, we're going to have negative 2 for the y. Oh wait, but this actually plays a role now. It's 1 times minus 5. We'll have minus 5 minus 2. That would be minus 7. All right, let's go another round on this. We'll just update our values as we go here, maybe making a little more room so it's easier to follow. We're going to have pi over 2. So the value inside the sine and cosine is actually going to be twice that, which is pi. And cos of pi is minus 1, sine of pi is 0. Going through these same kinds of calculations, we're going to have 3 minus 5. That's minus 2. And here we're going to be back to negative 2 again. And if we repeat this calculation one more time for the 3 pi over 4, what we're going to get is a 3 and a minus 2 plus 5, which is going to be 3. And interestingly, if we do pi, and do this calculation again, we're going to be exactly back where we started, 8 minus 2. So we can feel the circular aspect of this over this time interval, and it just makes sense to try to sketch this a little bit. Both x and y's are positive and negative, so we'll center ourselves here a bit in the middle. We need a fairly large scale, so let's go 4 and 8. Minus 4. And we'll keep the scale even. What we have is 8 minus 2. 8 minus 2 is here. And then we went to 3 minus 7. 2, 4, 6, 7. Then minus 2 minus 2. And then 3, 3. And then back to there. And we can see from there we essentially have a circle. Slightly skewed because of my sketching abilities, but we have a circle, and the direction was in the clockwise direction for this particular example. And we can see a number of important features tied into that. If we take a look at this distance here, it's 5. So is this, as a circle. Well, guess what? Both of those values there, if they're the same, are going to give us the radius of our circle. Why? Because we're taking our basic cosine sines and we're expanding the amplitude. We're enlarging the circle or shrinking the circle by whatever that coefficient is. And if we take a careful look at that point, which is at the center of all of this, literally the center of the circle, it is exactly at 3, negative 2. And so we can see that as these shifts that we're applying to the x and y components. we had the circle centered at the origin, but then we added 3 to all the x components. That shifted everything over by 3. Then we had all the y components we were computing before, and then we took all of them and subtracted 2 from them. Well, that shifted everything down by 2. And so we still have a circle, we just had the center moved up 3 in x and down 2 in y. Now the only other thing that was affected, and this is where we get into the derivatives, is the speed. Notice that we completed 1 revolution in pi seconds, whereas usually, regular sine and cosine, it takes 2 pi seconds. So what this 2 multiplier inside doesn't change the points that we cover, it changes how quickly we are covering them. We're going to look at how that plays a role when we go to design our own circular motion with uniform speed. Let's use those insights to help design a trajectory with properties that we want. For instance, a movement that is 8 meters in diameter with a center at 4, 7, presumably to match other equipment or other constraints. If we sketch that out, that would be like here for the point 4, 7, circle of radius 8, something like that, like so. And we're asked for a constant speed of 15 meters per second. We'll see how that plays a role in a moment. And the starting point starts at the bottom of the circle, the lowest y, so down here at time 0, and rotates clockwise. Well, if we do this correctly, that should be starting at the same x-coordinate, but the radius is 8, so we're going to subtract 8 to get down to there. That'll be -1 for our y-coordinate. What I find most helpful as a strategy here is an incremental approach. For instance, if we take a good starting point, which is our unit circle, which is the cos t sine t. We know what that function does. It has a unit circle centered at the origin. What we can then do is adapt it and then get the center, say, at the point 4, 7. And we saw in the last example that the center is defined by a shift in the x and a shift in the y, which gives us cos of t plus 4, and then sine of t plus 7. If we do that, we're going to achieve our center requirement. The other easy point is to change the radius. And for that, we simply have 8 times the cosine function. And we keep the plus 4, and notice there's no parentheses here. We're going to take all of our cosine values, make them 8 times larger. That'll give us the radius, and then we shift it when we're done as a separate operation. So there's no parentheses. The 8 simply goes with the cosine or the sine function in the y component. Still with a plus 7 for that component for the y. Now next up would be the starting point. Now this typically would start, well, it doesn't typically start, it will start at the cosine value being the highest, so it'll be out here, and then going counterclockwise. So let's tweak this so that we get our starting point down at the bottom. Well, how do we achieve that? Well, if you think about the math going on here, the reason we start at a large x value is because the cosine value is the one that moves you off of 0. Sine of 0 is 0, so we start at the 0 or the same y-coordinate as the center if we have a sine, and we have a larger x component. If we want to make the y component the larger thing, it's going to have a cosine on that. So we're going to try some, not guess and check, but thoughtful insight and check on the next page. So if we want the start at 4, -1, that means a negative y from the center at time 0. We would take all the same ingredients, the 8 and the 8, the plus 4, the plus 7, and the only thing we're going to change is we're going to make the y component the cosine. So we'll frame that in green here. But we don't want to add it So we're going to subtract the 8 cosine. And on the other side, we're going to start with the sine of t and just see what happens. So what this is going to do, if we take a quick look back at the diagram, is remember cosine, if we add a cosine, we go to the larger extreme of a particular axis. When we add 8, this is implicitly adding 8 cosine. If we did minus 8 cosine, we would start at the other extreme on the same circle. We want to start at the negative extreme, so we start at negative cos times 8 for the y component. And then we can check that at t equals 0. Let's call this r of t for a moment. We're going to have 8 sine 0, that's 0, plus 4, minus 8 times 1, plus 7, and sure enough, that is 4 negative 1. Next up, clockwise direction. Maybe it's happening, maybe it's not, we don't know. Let's see at a later time point. Let's take pi over 2. That'll be halfway, or sorry, 1/4 of the way around the circle at our uniform speed of 1 radian per second. And if we do that here, we're going to get r of pi over 2 is 8 sine of pi over 2 is positive 8. Cos of pi over 2 is 0. And that is 12/7. And if we take a look at our picture, we'll sketch it up here. We started down here at 4 negative 1. And then this is saying after a quarter cycle, we are going to end up over here. That would be counterclockwise. Well, how do we fix that without breaking anything else? If we take a look at our ingredients, we can't change the time 0 value, so we're going to keep that minus 8 cos of t plus 7. But what we can change is not the center. We need the center to be at x equals 4. But we can change the direction that we go in as time increases. So remember, this starts at 0 and gets positive. Well, only if we wanted to. We can just slide a little negative sign in front there and get minus 8 sine of t plus 4. And that's going to cause this whole trajectory to move in the negative direction for the x's initially. We're going to take 4 minus some stuff. We're going to head to the left, and that's going to correct our direction. And so this will rotate in a clockwise direction. Last but not least, we need to achieve the constant speed of 15 meters per second. We're going to copy this version of our function so far and see how that can be made to work with the desired speed. Now, one temptation would be to simply put the 15 into the inside of these functions here. However, even a quick thinking about regular circular motion, putting your physics hat on for a second, if we are doing 1 revolution per 6 seconds, or 2 pi seconds more precisely, if you imagine increasing the radius, that's going to have an influence. If you go around a circle that's 1 meter in radius in a certain speed, or in 6 seconds, that's going to be 1 speed. But if you had a 10 meter circle in exactly the same time, so 6 seconds around this huge circle, you're going to have a higher velocity. So how do those two factors interact? Well, that's why we developed all the calculus for the velocity calculations. We can actually get an exact formula for our speed. What we're going to do, though, is we're going to slide in a constant here, let's call it a, in both of these, because we saw that a multiplier inside the time helps to control the velocity. It doesn't tell you exactly what it is, but it's an element of it. And if that's r of t, then our velocity is going to be minus 8. Derivative of sine is cosine. We had an at in there. If we take the derivative of that, we're going to get an a coming out from the chain rule, and the derivative of the plus 4 actually goes away. It's just plus 0. And then we get minus 8 derivative of cos at. In fact, let's write this even more explicitly, so your intuition around derivatives makes more sense. So at is hiding inside the sine function, and at is hiding inside the cosine as well. That will give us minus 8 when we differentiate minus sine of at times a derivative of plus 7 is 0. It's derivative of a constant. Clean that up a little. And what we see is when we can factor out these 8's and a's, we can actually factor out a common minus 8 if we like. Minus 8a times cos of at sine of at. That is our velocity. And as we know, if we want a speed that is constant at 15 meters per second, we simply find the magnitude of that vector. Cos of at sine of at. And the nice thing about magnitudes is that if we have a multiplier, it just comes out front, it becomes positive. So we get 8a times the magnitude of cosine, but that's the square root of cos squared of at plus the square of that, sine squared of at, all square rooted. But lo and behold, there's our trig identity. Cos squared plus sine squared of the same angle, or same time value here, is always 1. And so we get our speed is equal to 8a. If we want speed to equal 15, we need 15 to equal 8a, or our a value equals 15 over 8. And so our final function is going to be this whole construction here, just moving things briefly. To make a little more room, we want for our r of t negative 8 times a sine function. That sine function is not just t, but 15 over 8t to get the right velocity, and then a plus 4 to define the center of the circle in the x direction. It centers at x equals 4. And then almost identically, cos of 15 over 8t for the y component, and then always shift it up by 7 to move the center of the circle up to 7.